Welcome to the Explainer. Sometimes you see a math problem that just looks impossible. Today, we're staring down one of those, a trigonometric proof that seems incredibly complicated. But I promise you, it's really just a puzzle waiting to be solved. So, let's get into it.
Okay, here it is, our challenge. Just look at that thing. It's a dense fraction, packed with cosines of all these different angles. It's kind of designed to be intimidating, right? To make you think, where in the world do I even start? Well, that's exactly what we're going to figure out, together, step by step.
So, let's stop thinking of this as some scary math problem. Instead, think of it like a mathematical escape room. It looks super complex on the outside, but we know that inside there are clues and keys hidden that will lead us straight to the solution. And like any good puzzle solver, the first thing we need is a solid strategy.
And our strategy is a classic for a reason: divide and conquer. We are not going to try to wrestle this entire beast into submission at once. No way. Instead, we're going to break it down into smaller, much more manageable pieces. Honestly, this is the secret to solving almost any complex problem you'll ever face.
So here's our game plan, and it's super simple. Just 2 steps. First, we're going to focus only on the top part of the fraction. That's the numerator. Once we've got that sorted out, we'll give the exact same treatment to the bottom part, the denominator. Ready to tackle step 1? All right, let's get this investigation started with the numerator. We're going to completely isolate it, forget everything else for a moment, and see what secrets it's hiding.
Here it is, all by its lonesome, just 4 terms. Now, our first move isn't to calculate anything, it's just to organize them. We need to group them in a clever way that lets us use some of the special tools we have in our trig toolbox.
And see, just a simple little rearrangement changes everything. By pairing them up like this, we've created 2 distinct little groups, 1 minus cos of 10 and cos of 40 minus cos of 50. Now, why is this so great? Because each of these groups perfectly matches the pattern of a well-known trigonometric identity. It's like we've just created 2 locks that we already have the keys for.
So here's our first key. It's for that 1 minus cos of 2 theta pattern. This is called a half-angle identity, and it lets us completely transform that expression into 2 sine squared of theta. And if you look at our first group, 1 minus cos of 10, it's a perfect match. Applying it is actually pretty simple. In our case, the 2 theta is 10, which means the theta must be 5, right? So 1 minus cosine of 10 transforms neatly into 2 sine squared of 5. Boom! First piece, simplified. Now for our second group, we need a different key. This one's a sum to product identity. And this is a really powerful tool because it lets us turn a difference of 2 cosines into a product of sines, which, as you'll see, is way easier to work with. So let's plug in our numbers. A plus B over 2 is just 40 plus 50 over 2, which is 45. And B minus A over 2 is 50 minus 40 over 2, which is 5. So just like that, cos of 40 minus cos of 50 becomes 2 sine 45 sine 5. And there we go, the second piece is simplified. So look at what we've done. By using 2 very specific identities, we've changed our complicated numerator into this much, much cleaner expression. Step 1 is officially complete. Now, let's see if we can pull off the same trick with the denominator. We are halfway home. Now we just apply the exact same strategy to the bottom of the fraction. We don't need a new process. We just need a slightly different set of keys for this new lock.
So here's our denominator. And again, the first thing we do is group the terms strategically. We'll pair up 1 plus cos 10, and then for the other 2, we'll pull out a negative sign to get minus cos 40 plus cos 50.
Hey, remember that half-angle identity from before? Well, it has a twin. For the denominator, we're using the 1 plus cos of 2 theta version. And notice this, a tiny change. Just a sign flip from minus to plus completely changes the result from sine squared to cosine squared. It's really elegant, isn't it? Okay, let's apply our new tools. First, using that cosine version of the half-angle identity, 1 plus cosine of 10 becomes 2 cosine squared of 5. Easy enough. Next, we use the sum to product rule for cosine of A plus cosine of B, which turns cosine of 40 plus cosine of 50 into 2 cosine of 45 cosine of 5. And with that, step 2 is done. Our denominator is officially unlocked. And now, this is the fun part. We did the heavy lifting, we simplified the top and the bottom separately. Now it's time to put them back together and see what we've actually created. Would you look at that? The original mess has transformed into this, and we can immediately spot some common factors.
Up top in the numerator, we can pull out a 2 sine phi, and down in the denominator, we can factor out a 2 cos phi. This is already looking so much better. And we can make things even simpler right away. The 2's cancel each other out. And what do you get when you have sine of 5 over cos of 5? Well, that's just tan of 5. So we can pull that term right out front, leaving us with just one final smaller fraction to deal with.
We are so close now. This little fraction right here is the very last piece of the puzzle. But it looks kind of familiar, doesn't it? It's a sum of sines on top and a difference of cosines on the bottom. We have the tools for this. We just have to apply our sum to product rules one last time.
And here it is, the beautiful cascade of simplification we've been working towards. When we apply the identities, the numerator becomes 2 sine of 25 cosine of 20, and the denominator becomes 2 sine of 25 sine of 20. And just look what happens. The 2's cancel, the sine of 25's cancel, and we're left with cosine of 20 over sine of 20, which is simply cot of 20. I mean, that is just beautiful.
After all those steps, breaking the problem down piece by piece, using our identities like keys to unlock each part, we finally arrived at the end, the final, elegant solution. We just combine our two simplified parts, that tan 5 we pulled out a few steps ago, and the cot 20 we just found. And that is our answer. All of that initial complexity, all those terms, just boiled down to tan 5 cot 20. Proof complete.
You know, this explainer wasn't really just about trigonometry. It was about a method, a way of thinking. This divide and conquer strategy that we used, it applies almost everywhere, from programming and engineering to just planning a big project or even learning a new skill. So what's a complex problem in your world that you could start solving today, one small piece at a time? Thanks for joining me on The Explainer.